Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
Beyond the boundaries that usually define planetary systems, space follows patterns that are broad, slow, and statistically regular. Stars in the Milky Way do not move at random. They orbit the galactic center in a flattened disk, sharing a general flow shaped by gravity accumulated over billions of years. This shared motion forms a background against which individual objects can be measured. In this outermost region, distances of vast interactions are rare and change occurs gradually. The interstellar medium contains thin gas-scattered dust and a population of solid bodies that drift between stars after being released from their systems of origin. These bodies inherit their initial motion from the stars and planets that expelled them, but over time their paths blend into the overall movement of the galaxy. This blending creates a quiet order. Most objects in this region travel at speeds similar to nearby stars, differing only by modest amounts. Extreme velocities require uncommon events and are statistically rare. Because of this, motion itself becomes a kind of record-preserving information about origin and history long after surface features have been altered. In this setting, the solar system is not isolated. The Sun moves through the local stellar neighborhood at a steady pace, carrying its planets and debris along with it. Around the Sun, other stars follow similar orbits, forming streams and associations that share related velocities. Together, these motions define what astronomers call the local standard of rest, an average reference frame describing how matter typically moves in this part of the galaxy. Objects that match this flow appear dynamically ordinary. Those that deviate stand out not because they are necessarily unusual in composition, but because their motion suggests a different past. Interstellar objects are expected to approach the solar system from many directions, but their speeds relative to the Sun are constrained by this broader context. Most should arrive neither extremely fast nor unusually slow, but within a range that reflects the galactic environment. The outer region is therefore governed by probability rather than exception. It is a place where countless small bodies pass unseen, their presence inferred more by theory than by direct observation. Light travels freely here, largely unimpeded, while solid objects remain dark unless they pass close to a star. Gravity dominates but gently. Encounters between small bodies are so infrequent that a single trajectory can persist unchanged for millions of years. When a star passes nearby, it can redirect a path, but such encounters are rare and usually subtle. Over long spans of time, this produces a population of wanderers whose motions encode averages rather than specific events. The galactic disk itself evolves slowly. Star formation rates rise and fall, spiral arms shift, and stellar populations migrate. As a result, the density and composition of interstellar debris change gradually. Younger regions contribute more freshly ejected material, while older regions contain bodies that have travelled longer and been processed by radiation for extended periods. The Sun's current location places it within a relatively calm portion of the disk, where stellar densities are moderate and relative velocities are not extreme. This context sets expectations for any interstellar visitor that enters the solar system. Before such an object feels the Sun's gravity, it is already defined by this outer order. Its approach speed, direction, and timing are shaped by the collective motion of stars rather than by any single interaction. Even before detection, these parameters limit what the object can be. The outer region does not care about surface texture or internal structure. It only preserves motion. Because of this, motion becomes the first filter through which an interstellar object is understood. An object whose velocity aligns closely with the local stellar flow appears consistent with long residence in the galactic environment. One whose motion is strongly misaligned suggests either a recent ejection or an origin involving unusual forces. This distinction is statistical, not absolute, but it provides a framework that guides interpretation without requiring speculation. The outer environment also determines encounter rates. The solar system sweeps through interstellar space, intersecting the paths of wandering bodies occasionally. Most pass far away unnoticed. Only those that come sufficiently close to the Sun become visible with current instruments. This visibility is brief on cosmic timescales. An interstellar object may be detectable for months or years, yet it may have travelled for billions of years before, and will continue for billions more after. The outer region therefore dwarfs the moment of observation. It establishes a perspective in which detection is an interruption rather than a defining event. From this perspective, unusual behaviour must be judged against long-term averages, not momentary impressions. The galactic background also influences expectations about composition indirectly. Planetary systems across the galaxy form under similar physical laws. While details vary the basic processes of disk formation, planet growth and dynamical scattering are common. This suggests that interstellar debris should mostly resemble material already familiar from the solar system, though processed differently depending on origin and age. The outer region does not encourage exotic assumptions, it encourages continuity. Objects released into interstellar space are the byproducts of ordinary planetary evolution filtered by survival over time. Those that persist are those that can endure radiation temperature extremes and isolation without rapid change. This endurance selects for stability long before observation begins. In this calm outer setting, classification begins not with labels, but with distributions. Motion is compared to motion speed to speed direction to direction. An object that fits comfortably within expected ranges does not immediately demand new categories. Instead, it invites closer measurement within established frameworks. An object that does not fit challenges those frameworks, but only after the baseline is firmly established. The outer region thus serves as a reference plane defining what is typical before attention turns inward. It is a region defined by patience. Processes unfold slowly and signals accumulate over time. Nothing here happens suddenly, and nothing announces itself loudly. This quietness is essential. It prevents premature conclusions by anchoring analysis in large-scale regularity. Only by understanding this outer order can deviations be meaningfully identified. As the solar system moves through the galaxy, it samples this environment continuously. Each interstellar object that passes nearby is one draw from a vast distribution shaped by billions of years of shared history. The outer region does not explain individual cases in detail, but it constrains them. It tells what is likely and what is rare, what requires special explanation, and what does not. In doing so, it prepares the ground for deeper examination. The focus remains wide, encompassing the collective behaviour of stars and debris rather than the properties of any single object. Within this breadth, order emerges not from design, but from accumulation. Gravity, time, and probability combine to produce patterns that are stable and predictable. Any object entering the solar system carries these patterns with it embedded in its motion. Before light is measured, before forces are analysed, before material properties are inferred, the object is already speaking through its trajectory. In the outermost region, that speech is quiet and statistical, but it is consistent. It establishes the calm backdrop against which any claim of unusual behaviour must be tested, ensuring that attention moves inward only after the widest context is fully accounted for. Within the broad galactic flow, individual planetary systems act as sources of solid debris, steadily contributing material to interstellar space over long spans of time. This population is not directly visible as a whole, but it is inferred from models of planet formation and from the structure observed within mature systems. During the early stages of a planetary system, a disk of gas and dust surrounds a young star. Within this disk, countless solid bodies form, collide, grow, and migrate. Not all of them remain bound. As planets accumulate mass, their gravity reshapes the disk, scattering smaller bodies inward and outward. Some collide and are destroyed, some are incorporated into planets or moons, and some are accelerated onto paths that exceed the escape velocity of the system. These escaped bodies become interstellar debris. This process is not rare. It is a natural outcome of planetary growth, especially in systems that form giant planets. Numerical simulations indicate that a significant fraction of the original solid mass in a disk can be ejected over time. Each system contributes modestly, but across the galaxy the total becomes substantial. The result is a diffuse population of objects ranging in size from grains to bodies, many hundreds of meters across, all traveling independently between stars. The properties of this population are shaped by selection, long before detection. Bodies that are fragile, highly porous, or rich in exposed volatiles are more likely to fragment, erode, or alter significantly during or after ejection. Those that survive intact are the ones that enter interstellar space already robust. Over time, this survival bias becomes stronger. Interstellar space is not violent, but it is persistent. Radiation thermal cycling near occasional stars and the absence of shielding slowly modify surfaces. Objects that cannot tolerate these conditions gradually change or disappear as recognizable solids. As a result, the population that remains after billions of years is not a random sample of what was ejected. It is a filtered one. Estimates of number density suggest that interstellar objects comparable in size to large asteroids may pass through the inner regions of planetary systems like the Solar System relatively frequently on astronomical timescales, though most remain undetected due to faintness and distance. Detection requires both proximity and favourable geometry. This means that observed objects represent a biased subset weighted toward those that are large, reflective enough to be seen, and dynamically accessible to survey instruments. This bias complicates classification. The observed behaviour of an interstellar object must be interpreted with the understanding that it is not representative of all such bodies, only of those that meet these observational criteria. Composition across the interstellar debris population is expected to be diverse, reflecting the range of environments in which planetary systems form. Some systems are metal-rich, others poorer. Some form close-in giant planets, others do not. These differences influence what kinds of material are scattered outward. However, the underlying physics of condensation, collision, and gravity remain the same. This suggests that while details vary, the broad categories of material should resemble those already known: rocky, icy, or mixtures of both modified by processing. Extreme compositions are not forbidden, but they are not required to explain the population. The debris population also evolves with galactic time. Early in the galaxy's history, star formation rates were higher, and planetary systems formed under different chemical conditions. Older interstellar objects may therefore carry signatures of earlier epochs, though these signatures are often masked by surface processing. Younger objects ejected more recently may retain more distinctive features, but are statistically less likely to have had their motion blended into the local stellar flow. This introduces a temporal gradient within the population, where age influences both physical state and dynamical behaviour. Classification schemes developed within the Solar System are challenged by this diversity and by the effects of long-term processing. Objects that would be called comets when bound to a star may appear inactive after extended exposure to interstellar conditions. Objects that resemble asteroids in behaviour may have formed in icy regions but lost accessible volatiles. The labels themselves become less informative when removed from their original context. What remains useful are measured properties, motion, brightness, variability, and response to external forces. These are the tools by which interstellar debris is understood. The population as a whole is therefore best described statistically rather than individually. Models predict distributions of size, velocity, and composition rather than specific outcomes. When an individual object is observed, it is compared against these distributions to assess how typical or atypical it is. An object whose properties fall near the centre of expected ranges does not demand reclassification of the population. An object that consistently lies at the edges or outside those ranges prompts closer scrutiny. Importantly, uncertainty is built into these expectations. Many parameters are poorly constrained because of limited observational data. The number of detected interstellar objects remains small, and each new detection significantly refines estimates. As a result, boundaries between categories are not sharp, they are probabilistic. This makes classification provisional, subject to revision as more data accumulate. The interstellar debris population also interacts with planetary systems it encounters, but usually weakly. Most fly through without close approaches to planets experiencing only the star's gravity. Rarely an object may be captured temporarily or permanently, but such events are uncommon. The typical interaction is brief and leaves the object largely unchanged. This reinforces the idea that observed behavior during a single passage reflects long-term properties rather than transient effects. In this context, the difficulty of classification does not imply anomaly. It reflects the fact that existing categories were developed for objects observed in situ within the solar system under repeated observation. Interstellar objects are seen once briefly and under constraints that limit available data. Their apparent refusal to fit neatly into established classes arises as much from observational limitation as from intrinsic difference. The population they belong to is broad, ancient, and only partially sampled. Within that population, continuity is expected to be greater than distinction. Section 2 thus establishes the interstellar debris population as a natural extension of planetary system evolution shaped by common processes and filtered by time. Any individual object observed within this population carries that history implicitly. Its properties must be evaluated against this background, recognizing both the diversity of origins and the uniformity imposed by long-term survival. Only after this population context is understood can attention narrow further from the many to the one from expectation to measurement, and from statistical background to specific behavior. He does not think of the object as a thing so much as a record. Every movement it makes is a sentence written in the grammar of gravity, every slight deviation a footnote left by forces encountered long ago. In space, nothing travels without remembering. Motion is memory. Velocity is history compressed into direction and speed. As the object continues its passage through the solar system, its trajectory becomes a readable archive, one that speaks quietly but persistently to anyone willing to listen long enough. The first memory it carries is age. Interstellar space is not kind to fragile travelers. Radiation erodes surfaces. Micrometeoroid impacts chip away at edges. Thermal cycling stresses material until weakness becomes fracture. Objects that do not possess internal coherence simply do not last. They fragment, disperse, dissolve into noise long before encountering another star. The object's continued integrity implies a deep past, measured not in millions but in billions of years. It has crossed regions where stars are born and die, where shock waves ripple through molecular clouds, where gravity itself is turbulent. It has endured. This endurance is not accidental. Its motion suggests that it has learned through countless encounters how to yield without breaking. Each close pass to a star would have reshaped its path, altering speed and orientation. Over time, such encounters tend to randomize trajectories. But the object's current motion shows coherence rather than scatter. That coherence hints at a long sequence of gentle interactions rather than a few catastrophic ones. It has not been violently expelled from a single system. It has been guided, nudged, refined by many. He considers the galactic environment the object has traversed. The Milky Way is not empty. It is threaded with spiral arms, dense with stars separated by quieter interarm regions. Passing through these zones subjects travellers to varying gravitational fields, changing radiation levels and shifting particle densities. To survive repeated passages requires more than luck. It requires structural resilience and a capacity to absorb energy without amplifying stress. The object's smooth motion through the solar system suggests that such resilience is not just present but optimized. The second memory is direction. When its velocity vector is transformed into a galactic frame of reference, it does not point randomly. It aligns loosely with the motion of nearby stellar populations, as if it shares a common dynamical heritage with stars that formed long ago and now drift together through the galaxy. This does not identify a birthplace, but it narrows the story. The object is not a refugee from a recent stellar catastrophe. It is a veteran of the galactic disk moving in step with ancient currents. He notices how its speed relative to the local standard of rest is modest. It is not racing ahead of the galaxy nor lagging far behind. It belongs to the flow. This is another improbability that refuses to be loud, yet accumulates weight through repetition. Objects ejected violently tend to carry extreme velocities, marking them as exiles. This one does not. It moves as though it has spent most of its existence in gentle orbit around the galaxy itself. The third memory is restraint. As the object approaches perihelion, the region of closest approach to the Sun, forces intensify. Solar tides stretch and compress. Radiation heats surfaces unevenly. Volatile materials, if present, would sublimate, producing jets that act like thrusters. Many small bodies betray their internal composition at this stage, their paths wobbling as hidden ices awaken. This object remains composed. Any non-gravitational effects are subtle, almost shy. Its motions suggest either a lack of volatiles or a structure that suppresses asymmetric activity. Either way, the result is the same control. Control is not consciousness here, it is consequence. The object's motion implies that its internal makeup distributes stress, evenly preventing localized failure. It is not a loose pile of debris barely held together. It is something more unified. That unity could be the result of slow accretion compaction, under repeated heating and cooling, or even partial melting and resolidification long before it entered interstellar space. The exact mechanism remains unknown, but the signature is clear. He reflects on how rare such coherence should be. Most small bodies are relics of violence leftovers from collisions that never fully healed. Their structures are porous, irregular, fragile. They survive because they have not been tested too often. This object has been tested repeatedly and remains intact. Its motion is the proof. The fourth memory is patience. Time scales in interstellar space are immense. To travel between stars at the speeds measured here requires millions of years. To wander the galaxy for billions of years without capture or destruction requires not just durability, but a kind of orbital wisdom. The object's path suggests it has avoided deep gravitational wells whenever possible. It has not lingered near stars long enough to be absorbed or shattered. Instead, it has passed at distances that allow exchange without entrapment. This behavior leaves an imprint. The distribution of its energies, the smoothness of its curve, the absence of scars in its motion, all point toward a long history of near misses rather than collisions. Near misses preserve. Collisions erase. The object's continued existence implies it has favoured the former almost exclusively. He wonders whether this preference emerges naturally over time. Objects that survive longest are those that by chance adopt trajectories minimising risk. Over billions of years, the population of survivors would be biased toward those that move carefully. The object before him may simply be one of the last representatives of a vast, mostly vanished population. Its organisation then is not unique but rare, because disorder does not persist. The fifth memory is silence. Despite its long journey, the object carries no obvious sign of recent trauma. No sudden changes in velocity, no abrupt directional shifts. Its past, at least in the recent astronomical sense, appears calm. This calmness is deceptive. It does not mean nothing happened. It means whatever happened was absorbed without leaving sharp edges. As the object continues through the inner solar system, its motion remains consistent with this narrative. The sun bends its path but does not dominate it. The planets whisper but do not seize it. The object listens, adjusts, and moves on. Each interaction adds another layer to its memory, another refinement to its trajectory. He realizes that motion is the only biography available. There is no photograph that can reveal where the object has been. There is no sample to analyze, no surface to touch. There is only the curve it traces against the stars, and that curve tells a story of survival through moderation of endurance through balance. The phrase memory carried by motion feels apt. The object remembers every force that failed to destroy it. Its present behavior is shaped by all the dangers it has already avoided. In this way, the object is not merely passing through the solar system, it is sharing its past encoded in velocity and direction for a brief moment before moving on. He senses that this memory challenges assumptions. Interstellar space is often imagined as a realm of chaos, where objects are flung randomly and survive only briefly. This object suggests another possibility that given enough time, chaos filters itself, leaving behind travellers that are quiet, stable, and deeply organised. As the object recedes from the sun's strongest influence, its path begins to straighten again, preparing to return to interstellar space. The solar system will leave its mark subtle but real, adding one more chapter to a story already unimaginably long. Soon the object will carry that chapter onward beyond the reach of observation. In the end, what remains is not certainty but a shift in perspective. The object is not remarkable because it is mysterious. It is remarkable because it is consistent. Its motion is a calm thread woven through the noise of the universe. And in that consistency it reminds him that order is not always imposed. Sometimes it is simply what survives long enough to be seen. Beyond the immediate pull of the sun, the environment through which the object moves becomes clearer in scale and structure. The solar system is not a single region, but a layered space shaped by gravity, radiation, and magnetic influence. The object enters this space from far outside, crossing boundaries that are invisible yet measurable. Its first passage is through the heliosphere, a vast bubble inflated by the solar wind where charged particles stream outward from the sun and press against the surrounding interstellar medium. This boundary is not rigid. It flexes and breathes as solar activity rises and falls, but it still marks a transition from one regime of space to another. The object crosses it without pause, its motion unchanged in any dramatic way. That calm passage already conveys information. The heliosphere contains a diffuse plasma and a weak magnetic field carried outward by the solar wind. For fragile objects, long exposure to this environment can alter surfaces, sputter atoms away, and induce electrical charging. Yet the object shows no sudden change in rotation or path that would suggest strong interaction. Its mass and structure appear sufficient to make these effects negligible over the brief time spent crossing this outer layer. This indicates that whatever processes shape the object did so in environments at least as harsh as this, if not more so. As the object moves inward, the sun's gravity gradually becomes the dominant force. The motion follows a predictable curve, one that can be described entirely by classical mechanics. There is no need to invoke exotic physics or unknown forces. The path fits within established models once the object's incoming velocity and direction are known. What draws attention is not that gravity works, but how cleanly it works here. The object behaves like a single coherent mass, not like a cloud of fragments responding unevenly. This again reinforces the picture of internal unity. The region between the outer planets and the inner solar system is sparsely populated yet not empty. Dust grains, remnants of comets, and the distant gravitational influence of giant planets all contribute subtle perturbations. Over time, these small influences can accumulate, especially for objects that linger. This one does not linger. Its trajectory carries it through, efficiently minimizing exposure. The time it spends in this region is short compared to the millions of years it has likely spent between stars. As a result, the solar system has little opportunity to erase the signatures of its earlier journey. He considers the role of the giant planets. Their gravitational fields extend far beyond their visible disks, creating regions where passing objects can be deflected, slowed, or captured. Jupiter in particular acts as both gatekeeper and sculptor, altering the architecture of the solar system by scattering small bodies. Many interstellar visitors would experience noticeable deviations if they passed close enough. This object's path suggests it avoids such deep encounters. Its route threads between these wells of gravity with precision that appears remarkable only because of how narrow the margins can be. Precision here does not imply intention. It implies probability filtered by time. Objects that pass too close are removed from the sample, either captured or destroyed. Objects that pass at safer distances continue. Over billions of years, the surviving population is dominated by those whose paths naturally avoid extremes. This object belongs to that population. Its current passage is simply another iteration of a process that has worked many times before. As it approaches the inner solar system, the intensity of solar radiation increases. Light carries momentum, and when it strikes a surface unevenly, it can produce a small but measurable force, known as radiation pressure. For very light or very irregular objects, this can alter trajectories. Observations here show that any such effect is minimal. The object's response to sunlight remains consistent with its estimated mass and cross-sectional area. There is no need to assume unusual reflectivity or extreme shapes to explain the data. Ordinary physics suffices. The thermal environment also changes. Temperatures rise as distance to the sun decreases, heating the surface and potentially driving off volatile compounds. In many small bodies, this process reveals internal layering and composition through outgassing. Jets form where sunlight penetrates cracks or porous regions, creating thrust that alters motion. In this case, such activity is either absent or balanced in a way that produces no strong net effect. The object does not behave like a typical comet. This absence is informative but not conclusive. It suggests either depletion of volatiles or a structure that traps them effectively. He notes that both possibilities are consistent with long exposure to interstellar space. Over immense timescales, volatiles near the surface would gradually be lost, leaving behind a refractory exterior. Alternatively, repeated heating and cooling could sinter material together, sealing pores and reducing permeability. In either scenario, the result is the same: a body that remains dynamically quiet when warmed by a star. The solar system itself adds another layer of context. It is a relatively calm environment compared to regions near massive stars or dense clusters. The sun's gravity is stable, its radiation moderate. For the object, this passage may be among the gentler stellar encounters it has experienced. This gentleness allows observers to study it without the confounding effects of extreme stress. The object reveals itself not through dramatic reactions, but through restraint. As the object passes through the plane of the planets, it encounters a region shaped by long-term dynamical order. Planetary orbits lie roughly in a disk, a relic of the solar system's formation. Interlopers crossing this disk often do so at steep angles, spending little time within it. This object follows that pattern. Its inclination relative to the planetary plane is high, reducing the chance of close encounters. This geometry further limits interaction, preserving the object's original state as much as possible. He reflects on how many filters the object has already passed. To arrive here in observable form, it must survive formation, ejection, interstellar travel, and now stellar passage. Each stage removes countless others. What remains is not representative of all that once existed, but of what endures. The solar system in this sense functions as a testing ground rather than a source. It does not create the object's properties, it reveals them. The clarity of this revelation depends on restraint. If the object were violently active or structurally unstable, interpretation would be difficult. Noise would dominate the signal. Instead, the object offers a clean case. Its motion through the solar system is smooth, its response to force is measured and predictable. This allows the focus to remain on deeper questions of origin and history without distraction. As it moves past the region of stronger solar influence, the object begins the long process of departure. The Sun imparts a slight change in direction and speed enough to alter the object's future path through the galaxy, but not enough to bind it. This alteration becomes part of the object's memory, encoded alongside countless others. The solar system's contribution is modest yet permanent. In this outer to inner exploration, the environment itself emerges as a collaborator. Space is not empty backdrop, but an active participant shaping motion through layered influences. The object's behavior within these layers demonstrates compatibility rather than conflict. It fits within the solar system's physical rules without strain. That fit, quiet and unremarkable on the surface, is precisely what makes it valuable. It allows the environment to be read through the object and the object to be understood through the environment. By the time the object leaves the inner regions behind, it carries with it an imprint of the Sun's domain, subtle but measurable. Observers record this imprint not as a dramatic transformation, but as a continuation of order. The object enters, responds, and exits. The solar system closes behind it unchanged, while the object moves on still intact, still coherent, still following a path that can be traced but not fully retraced. With the solar environment now receding from prominence, attention turns inward to the object itself, not its deep interior yet, but the outermost material that meets space directly. This surface layer is the boundary where history and environment exchange energy. It is where radiation arrives, where particles strike, where heat flows in and out. Everything known about the object's composition begins here, inferred not by touch, but by the way light interacts with matter. Observations show that the object reflects very little sunlight. Its surface is dark, absorbing most of the energy that reaches it. Such darkness is common among bodies exposed to space for long periods. Over time, energetic radiation alters simple compounds, breaking molecular bonds and allowing carbon-rich residues to accumulate. These residues form complex, stable materials that tend to be dark and spectrally bland. The object's low reflectivity fits comfortably within this pattern. It does not require unusual chemistry, it requires time. The colour of the reflected light provides further clues. Measurements suggest a surface that is not strongly red or blue, but muted with gentle slopes across visible wavelengths. This indicates the absence of fresh ice or exposed minerals that would produce sharper spectral features. Instead, the surface appears weathered, homogenized by countless small impacts and prolonged irradiation. Micrometeoroids travelling at high speeds strike the surface, melting or vaporizing tiny regions. Each impact redistributes material, gradually smoothing contrasts. Over billions of years, this process creates a skin that is chemically and optically uniform. He considers how such a surface forms. In young planetary systems, small bodies often contain abundant volatiles mixed with dust and rock. When these bodies remain near a star, heat drives activity that refreshes the surface, exposing new material. In interstellar space, this refreshing process is absent. Instead, the surface ages without interruption. Radiation penetrates to shallow depths, altering chemistry, but leaving structure largely intact. The result is a crust that is both protective and revealing. It seals the interior while carrying the imprint of external conditions. The thickness of this altered layer is uncertain, but models suggest it could extend from millimeters to several meters, depending on composition and exposure time. Beneath it, material may be less processed, preserving older chemical signatures. The surface, however, dominates interaction with the environment. It controls thermal behavior, electrical charging, and response to radiation pressure. The object's calm passage through the solar system implies that this surface layer manages these interactions effectively. Thermal measurements indicate that the object heats and cools without dramatic gradients. This suggests a surface that conducts heat, slowly spreading energy over time rather than concentrating it. Porous materials, loosely packed grains, or fractured rock can produce such behavior. They trap heat in voids and release it gradually. This thermal inertia, a measure of how resistant a surface is to temperature change, appears moderate. It is neither so low that the surface flashes hot and cold, nor so high that it behaves like solid metal. Again, the value falls within expected ranges for small-aged bodies. As the object rotates, different regions face the Sun in turn. If the surface were highly irregular or compositionally patchy, this rotation could produce measurable changes in brightness. Observations show variations, but they are smooth and periodic, consistent with an elongated shape rather than dramatic surface contrasts. This implies that the material properties are broadly similar across the surface. There are no large patches of ice or reflective minerals abruptly altering the light curve. The object presents a consistent face to space even as it turns. He reflects on how rotation itself shapes the surface. Over long timescales, centrifugal forces can redistribute loose material, moving it toward regions of lower effective gravity. For elongated objects, this can lead to accumulation along certain axes, smoothing extremes. Impacts also play a role, shaking material loose and allowing it to settle. The end state is often more regular than the starting point. The object's surface may be the product of such gradual self-organization driven entirely by physics. The absence of detectable gas or dust surrounding the object during its solar passage reinforces this picture. If volatile rich layers were exposed, heating would produce a visible coma or tail. Their absence does not mean volatiles are completely absent, but it suggests they are either deeply buried or depleted. Burial could occur if an insulating crust thickened over time, trapping ices below. Depletion could occur if repeated weak heating events slowly removed accessible volatiles long ago. Both outcomes are consistent with interstellar residence measured in billions of years. Electrical effects also come into play. Ultraviolet light can eject electrons from surfaces, charging them positively. In plasma environments, differential charging can create forces that loft dust or alter trajectories. The lack of observed dust activity suggests that the surface either does not accumulate extreme charge differentials, or is cohesive enough to resist electrostatic lifting. This again points to a surface that has been compacted or cemented by long-term processing. The composition inferred from spectra remains limited in detail. Broad features hint at organic rich material, possibly mixed with silicates. There is no clear evidence for exposed metals or crystalline ice. The surface appears primitive but not pristine. It has been altered but not transformed into something unrecognizable. It retains the basic character of early solar system material while carrying the scars of deep time. He notes that this balance is important. Too much alteration would erase information about origin. Too little would imply youth. The object sits between these extremes. Its surface tells a story of long exposure without catastrophic resetting. It is old, but not obliterated. As the object moves away from the Sun, the surface cools again, returning to the deep cold of interstellar space. Any heat absorbed during passage diffuses inward or radiates away. No dramatic phase changes occur. The surface remains stable. The solar system leaves no visible mark beyond what careful measurement might detect. This stability allows the surface to act as a reliable interface between the object and its surroundings. It filters interactions, moderates responses, and preserves internal coherence. In doing so, it enables the object to behave as a single body rather than a fragile assemblage. In the outer to inner progression, the surface is the first layer of material reality. It is where external forces meet internal structure. What is learned here sets boundaries on what lies beneath. The surface suggests age, processing, and restraint. It does not yet reveal composition in detail, but it constrains possibilities. It narrows the range of stories that can be told without inventing new physics or improbable histories. As observation continues, the surface remains quiet. It doesn't flare, shed, or fracture. It absorbs attention precisely because it refuses drama. In that refusal, it communicates more clearly than any outburst could. The object's surface is not a spectacle. It is a record written slowly, read carefully, and never fully erased. Moving one layer inward, attention shifts from the surface itself to the bulk properties that govern how the object behaves as a whole. This region is not directly visible, yet it leaves measurable traces in motion, rotation, and response to external forces. Mass density and internal distribution do not announce themselves loudly, but they shape every interaction. From these effects, a picture begins to form of what the object is like beneath its weathered skin. The first constraint comes from acceleration. As the object passes through the solar system, its trajectory follows gravity with remarkable fidelity. Any deviation from a purely gravitational path would suggest either extremely low mass, unusual surface properties, or strong internal activity. Observations show that such deviations are minimal. From this, a lower limit on mass can be inferred. The object cannot be a thin shell or a loosely bound cloud. It must possess sufficient bulk to resist being pushed around by sunlight alone. Density follows from this reasoning. Given the observed size estimates derived from brightness and assumed reflectivity, the mass implies a density consistent with solid material mixed with voids. It is not dense like metal, nor diffuse like a swarm of dust. It occupies the middle ground, common to many small bodies, rock and carbon-rich compounds interspersed with empty space. This porosity is important. It allows the object to absorb shocks without shattering and to manage thermal stress without cracking catastrophically. He considers how such a structure forms. In the early stages of planetary system evolution, small grains collide and stick, forming aggregates. Over time, these aggregates grow compacting under their own gravity and through repeated impacts. If growth proceeds gently, porosity remains. If collisions are violent, material is pulverized or melted, reducing void space. The object's inferred properties suggest a history dominated by low-energy interactions. It grew but slowly. It was shaped but not smashed. Rotation provides another window inward. The object rotates steadily with no evidence of tumbling or chaotic spin states. Chaotic rotation often arises when a body experiences recent collisions or strong asymmetric forces. Stability suggests long-term evolution without major disruption. Over time, internal friction damps complex motions, leaving a simple rotation around a principal axis. The object appears to have reached this state long ago. Its rotation is not youthful, it is settled. The rotation period, while not extreme, is fast enough to place limits on internal strength. If the object were held together only by weak gravity, rapid rotation would cause it to shed material. The absence of such shedding implies some degree of cohesion. This cohesion could arise from material strength from interlocking grains, or from sintering where heat causes partial bonding. The exact mechanism remains uncertain, but the consequence is clear. The object behaves as more than a loose pile. Internal temperature also plays a role. Far from stars, the object spends most of its existence near the background temperature of space, only a few degrees above absolute zero. In such cold conditions, chemical reactions slow dramatically. Materials become brittle, yet also stable. When the object occasionally approaches stars, heating penetrates only shallow depths. The interior remains cold, preserving its structure over immense timescales. This thermal isolation further supports long-term survival. He reflects on the distribution of mass within the object. If mass were unevenly distributed, rotation would reveal it through wobble or changes in brightness unrelated to shape. The observed light curve suggests elongation but not strong internal asymmetry. This points to a relatively uniform internal makeup along its length. Such uniformity again favours gradual formation and long-term evolution rather than recent assembly from fragments. The question of whether the object contains ice beneath its surface remains open. Ice could exist in pockets or layers insulated by the outer crust. If present, it contributes to mass without strongly affecting surface behaviour. The lack of activity during solar passage suggests that any ice is either scarce or well shielded. Shielding requires thickness and cohesion. Thin or fractured layers would allow heat to penetrate more deeply, triggering outgassing. The object's calm response argues against that scenario. Mechanical strength emerges as a central theme. The object must withstand tidal forces during stellar encounters, internal stress from rotation, and cumulative damage from impacts. Its continued integrity implies that these stresses remain below critical thresholds. This does not mean the object is rigid like steel. It means its structure distributes stress efficiently. Porosity can be an advantage here, allowing deformation without fracture. Voids collapse, slightly absorbing energy. Cracks blunt rather than propagate. He notes that such structures are common in nature. Many asteroids within the solar system exhibit similar properties despite very different formation histories. What distinguishes this object is not that it has these traits, but that it has retained them over far longer times and through far more varied environments. The internal region, invisible yet decisive, acts as the backbone of survival. The object's response to tidal forces during its closest approach to the Sun offers additional insight. Tidal stress stretches the body along the line toward the Sun while compressing it laterally. For weak bodies, this can lead to fragmentation. No such fragmentation is observed. The object emerges intact, suggesting that internal cohesion exceeds the tidal stress encountered. Given the Sun's mass and the object's distance at closest approach, this sets a meaningful lower bound on strength. Electrical conductivity within the interior also matters, though indirectly. Charge accumulation on the surface can redistribute through conductive pathways, preventing large potential differences. If the interior were extremely insulating, surface charging might lead to dust lofting or structural stress. The absence of such effects hints at least modest conductivity, possibly through carbon-rich materials or mineral grains in contact. As the object rotates and travels, its internal region remains largely unchanged. There is no engine, no internal heat source driving evolution. Radioactive heating, significant in larger bodies, is negligible here. Time passes without transformation. This stasis is itself informative. It means the object seen today is likely very similar to the object that entered interstellar space long ago. Its interior is a time capsule, not because it is sealed perfectly, but because nothing has been energetic enough to disturb it. In the outer to inner sequence, this layer marks the transition from interaction to essence. The surface negotiates with space. The interior defines what the object can endure. From the constraints observed so far, a consistent picture emerges: moderate density, significant porosity, stable rotation, and sufficient cohesion. None of these properties are exotic. Together they form a combination that is rare only because survival is rare. He recognizes that many uncertainties remain. Without direct sampling, composition and structure cannot be pinned down precisely. Yet the range of possibilities is already narrow. The object cannot be hollow, cannot be flimsy, cannot be freshly assembled. Its interior tells a quiet story of balance achieved early and maintained over time. As the object continues its journey away from the Sun, the internal region remains as it was carrying forward the same mass, the same structure, the same quiet strength. Whatever environments await it next, they will test these properties again, and again only those that fall within a narrow band of resilience will persist. Going one step further inward, attention narrows from bulk properties to the materials themselves, not as isolated substances but as mixtures shaped by long exposure to space. This region is not a core in the planetary sense but a distributed interior where grains, compounds and voids coexist. The question here is not what single material dominates, but how different materials interact over time to produce the stability already observed. The starting assumption, grounded in studies of small bodies and interstellar matter, is that the object forms from a blend of silicate minerals and carbon-rich compounds. Silicates provide mechanical strength and resistance to heat, while carbon-based materials offer flexibility and chemical stability under radiation. Together they create a matrix capable of enduring extreme conditions without catastrophic failure. This combination is common in primitive bodies, but its persistence over interstellar timescales is less common. Within this matrix, grains range widely in size. Fine dust fills gaps between larger fragments, increasing contact points and distributing stress. Larger clasts provide rigidity and mass. Over time, repeated low-level heating and cooling cycles cause these grains to settle and rearrange. Edges round slightly, contact areas increase. This process, known as sintering, strengthens the structure without requiring melting. It occurs slowly, driven by thermal energy, just sufficient to allow atoms to migrate across grain boundaries. In interstellar space, such conditions arise during brief stellar encounters repeated over millions of years. He considers how carbon-rich material behaves under these conditions. Simple ices once present would have been altered early, either lost to space or transformed into more complex molecules. Radiation breaks bonds, allowing fragments to recombine into stable, irregular networks. These networks resist further change. They darken surfaces, but within the interior they also act as binders, gluing mineral grains together. This chemical evolution increases cohesion while reducing volatility. The object becomes less reactive over time, not because it is protected, but because it has already reacted as much as it can. The presence of voids remains important. Complete compaction would make the object brittle, prone to cracking under stress. Retained porosity allows deformation without fracture. When tidal forces stretch the object, voids compress, slightly absorbing energy. When impacts occur, shock waves dissipate rather than focusing. This balance between solidity and emptiness is a recurring theme in long-lived small bodies. The object appears to have reached this balance early and maintained it. He reflects on the role of water ice, often central to discussions of small bodies. If water ice exists here, it is likely trapped in isolated pockets or bonded chemically within minerals. Pure ice near the surface would not survive interstellar radiation for long. Deeper ice could persist, but only if shielded by a thick overburden. In that case, it contributes mass and thermal buffering without driving activity. The object's behavior allows for this possibility but does not require it. The material story works with or without ice. Mineralogical diversity also matters. Silicates can be crystalline or amorphous. Crystalline forms indicate heating above certain thresholds, while amorphous forms preserve low-temperature origins. The object may contain both, reflecting a mixed history. Early formation in a cold environment could produce amorphous material. Later brief heating events could crystallize portions without resetting the whole. Such partial processing aligns with a long, uneventful journey, punctuated by mild encounters. Electrical and thermal properties emerge from this mixture. Carbon-rich phases provide pathways for charge movement, preventing extreme buildup. Silicates slow heat flow, moderating temperature changes. Together they create an interior that responds smoothly to external forcing. Nothing reacts quickly, nothing amplifies disturbance. This internal damping is key to the object's calm exterior behavior. He notes that material evolution does not stop once the object enters interstellar space. Cosmic rays penetrate deep, altering chemistry slowly but persistently. Over billions of years, even interior regions experience change. Yet this change trends towards stability. Reactive compounds are transformed into inert ones. Fragile structures are replaced by robust networks. The object becomes chemically quieter with age. This chemical aging parallels the dynamical aging already inferred from motion. The distribution of materials along the object's length also deserves attention. An elongated shape suggests that material properties are consistent throughout, rather than concentrated at one end. Large internal contrasts would lead to differential erosion or deformation over time. The absence of such effects implies a relatively uniform mixture. This uniformity does not require precise initial conditions. It can arise naturally as weaker regions fail early, leaving behind those with balanced composition. He considers whether the object could be a fragment of a larger body. Fragmentation typically produces sharp edges, irregular internal structures, and residual stress. Over time, some of these signatures fade, but complete erasure is unlikely without substantial reprocessing. The object's inferred internal coherence argues against recent fragmentation. If it is a fragment, it must be an ancient one broken off so long ago that subsequent evolution has smoothed its internal contrasts. Material strength, chemical stability, and porosity together define the object's character at this layer. None alone would suffice. Strong material without porosity would crack. Porosity without cohesion would collapse. Chemical stability without mechanical strength would erode. The object survives because it combines all three in moderate amounts. This moderation again appears as a recurring outcome of time acting as a filter. As the object moves farther from the sun, internal temperatures return to their baseline. Any minor rearrangements induced by heating settle back into equilibrium. There is no memory of stress beyond what has already been absorbed into structure. The interior remains as it was slightly altered, slightly strengthened, but fundamentally unchanged. In the outer to inner progression, this material layer deepens understanding without introducing drama. It explains how surface behavior and bulk motion arise naturally from composition and structure shaped over immense time. The object does not require unusual substances or unknown processes. It requires patience, exposure, and survival. He recognizes that this inward step brings the narrative close to its limits. Beyond this speculation would risk outrunning evidence. What can be said is bounded by what the object reveals indirectly. At this level, the picture is consistent and complete enough to stand. The materials inside the object are ordinary, but their arrangement and history are not. They reflect a long negotiation with space that favours balance over extremes. The object carries this material architecture onward unchanged by its brief encounter with the solar system. Whatever region it enters next, the same mixture of grains, compounds, and voids will meet new conditions. As before, survival will depend not on novelty, but on the quiet adequacy of what already exists. The inward path now reaches a level where scale becomes subtle and evidence grows indirect. Here the focus shifts from materials as mixtures to the processes that act within them at microscopic levels. These are not processes that reshape the object quickly or visibly. They work slowly, altering bonds, redistributing stress, and setting limits on how change can occur. Over long spans of time, these quiet mechanisms decide whether an object remains coherent or slowly unravels. At this scale, radiation is one of the dominant influences. High-energy particles move freely through interstellar space, originating from distant supernovae and energetic stellar events. When they strike solid matter, they penetrate deeply, displacing atoms and breaking chemical bonds. Each individual interaction is minor, but over millions and billions of years, the cumulative effect becomes significant. Materials that cannot tolerate this steady bombardment degrade. Those that can adapt chemically and structurally persist. Within the object, radiation alters carbon-based compounds first. Simple molecules fragment and recombine, gradually forming complex irregular structures that are resistant to further change. These structures distribute energy efficiently, preventing localized damage from spreading. Silicate minerals respond differently. Radiation can create defects in crystal lattices, but these defects often remain isolated, locked in place by the surrounding structure. The mixed composition allows damage in one component to be absorbed by another, limiting overall impact. He considers how this gradual alteration affects mechanical strength. Radiation damage can weaken materials initially, but over time it can also lead to hardening as reactive sites are exhausted. Once a material reaches a chemically stable state, further radiation produces diminishing change. The object appears to have reached this plateau long ago. Its interior no longer evolves rapidly. It has entered a phase of slow equilibrium, where alteration continues but does not accumulate into instability. Thermal cycling contributes to this equilibrium. Each encounter with a star introduces heat followed by long periods of cold. At the microscopic level, repeated expansion and contraction encourage atoms to settle into lower energy configurations. Grain boundaries adjust, stresses relax. Over many cycles, the structure becomes more tolerant of temperature change. Sudden heating no longer produces large internal gradients. Energy spreads gently through the network of grains and voids. Another quiet process is diffusion. Even at very low temperatures, atoms can migrate slowly along defects and interfaces. Over geological timescales, this movement smooths sharp contrasts in composition and stress. Pockets of weakness are reinforced. Sharp boundaries blur. The object becomes more uniform internally, not because it was built that way, but because time erases extremes. This internal smoothing is invisible to observation, yet it shapes everything that can be observed. He reflects on the role of microfractures. Impacts and tidal stresses inevitably create tiny cracks. In young or brittle materials, these cracks propagate, leading to fragmentation. In the object, microfractures likely form but do not grow unchecked. Porosity interrupts them. Grain boundaries deflect them. Chemical alteration can even heal them as reactive surfaces bond under pressure and heat. The result is a structure that tolerates damage without failing. Electrostatic effects also operate at small scales. Charged particles embed themselves within materials, creating local fields. In conductive or semiconductive networks, these charges redistribute, preventing large buildups. In insulating regions, they remain trapped but isolated. The mixed nature of the object's interior prevents runaway effects. No region accumulates enough stress to drive large-scale change. The presence of trace elements matters here. Even small amounts of metals or salts can alter electrical and thermal behavior significantly. While direct evidence is lacking, such trace components are common in primitive materials. Their inclusion would further enhance internal regulation, allowing the object to dissipate energy smoothly. Again, nothing exotic is required. Ordinary complexity suffices. He notes that these microscopic processes are indifferent to location. They operate the same way in interstellar space as within the solar system, differing only in rate. Near the Sun, higher temperatures accelerate diffusion and relaxation slightly. Far from stars, radiation dominates. Over the object's lifetime, these influences average out, producing a stable internal state that changes only slowly. The concept of aging becomes relevant here. Aging is not decay in this context. It is convergence towards stability. Materials that survive longest are those that approach a state where further change is difficult. The object appears to have aged well. Its internal processes no longer introduce new vulnerabilities. They close them. He considers whether this internal calm could ever be disrupted. Only extreme events would suffice. A close encounter with a massive star, a strong tidal interaction, or a high-velocity collision could overwhelm the slow processes described here. The object's continued existence implies that such events have been avoided or survived. Probability again plays its role. Many objects are lost. This one remains. At this depth of analysis, the distinction between environment and object blurs. The object's internal processes are shaped by the environments it has passed through, but they also determine how it responds to new ones. There is feedback but not intention. Physics alone governs the exchange. Over time, feedback drives systems toward configurations that minimize stress. The object embodies such a configuration. He recognizes that this layer of explanation completes a chain. Large-scale motion reflects bulk properties. Bulk properties arise from material mixtures. Material mixtures behave as they do because of microscopic processes acting over time. Each level constrains the next. None require speculation beyond established physical principles. The object's behavior remains unusual only in how clearly it fits within these principles, without excess. As the object moves onward, microscopic processes continue their quiet work. Radiation strikes, atoms shift, bonds break and reform. Nothing dramatic occurs. This constancy is the point. The object does not need to change to survive. It has already changed enough. In the outer to inner path, this is the innermost region that can be discussed without crossing into conjecture. Beyond this lie questions of exact chemical inventories and atomic arrangements that cannot be resolved from afar. What can be said is that the object's smallest-scale processes favour stability over transformation. They damp disturbances, heal damage, and resist extremes. He senses that this inward journey has reached a natural pause. The object's behaviour from galactic motion down to microscopic interaction aligns with a single narrative of endurance through moderation. The inner workings do not contradict the outer signs. They support them quietly, consistently, and without spectacle. The object continues on its path, carrying within it a microscopic order shaped by time radiation and restraint. This order does not announce itself. It simply persists layer upon layer long after observation ends. With the internal processes described, the attention shifts back outward slightly to the way the object presents itself through motion and light together. Rotation and shape form a bridge between interior and surface. They are not directly observed as solid geometry, yet they can be inferred with care from repeating patterns in brightness. Each turn of the object carries information about symmetry, balance, and how mass is distributed along its length. As the object rotates, the amount of sunlight it reflects toward observers changes. These changes are regular, repeating over a consistent period. Such periodicity indicates a stable rotation state rather than a chaotic tumble. Tumbling objects show irregular overlapping cycles as they rotate around multiple axes. Here the signal is simpler. The object spins around a principal axis, one that has likely remained the same for a very long time. This stability reflects both internal damping and an absence of recent disruptive events. The amplitude of brightness variation provides the first clue to shape. Larger variations suggest a more elongated form where the projected area changes significantly during rotation. Smaller variations indicate a shape closer to spherical. The object's light curve shows moderate to strong variation consistent with an elongated body. It does not require extreme proportions, but it is clearly not round. The elongation appears smooth rather than jagged, implying a continuous outline rather than sharp edges or major protrusions. He considers how such shapes arise. In early formation stages, accretion tends to produce irregular forms. Over time, collisions and internal adjustments smooth those irregularities. Rotation itself encourages elongation along one axis, especially for bodies with modest cohesion. Material migrates slowly under centrifugal effect, settling into configurations that minimize energy. The result is often a stretched but smooth shape. The object fits comfortably within this expectation. The orientation of the rotation axis also matters. Observations suggest that the axis is not aligned in any special way with the object's trajectory through the solar system. This randomness is expected. Over interstellar timescales, torques from radiation and gravitational encounters would gradually reorient the axis. Any initial alignment would be lost. The present orientation reflects the cumulative effect of many small influences rather than a preserved original state. He reflects on the forces that can alter rotation. Radiation from stars can produce a torque if the surface reflects or emits heat unevenly. This effect, known in small bodies, can spin them up or slow them down over time. The object's rotation rate does not appear extreme. It sits within a range that suggests such torques have acted but not driven it to instability. This again implies a surface and shape that distribute energy fairly evenly, preventing runaway acceleration. The rotation period also constrains internal strength. Faster rotation increases centrifugal stress. If the object were weak, it would deform or shed material. The observed period falls below the threshold where disruption would occur for a body with modest cohesion. This reinforces earlier conclusions about internal structure. Rotation, shape, and material properties form a consistent set. None contradict the others. Brightness variations also encode information about surface uniformity. Sharp dips or spikes would indicate localized reflective regions or deep concavities. The observed light curve is smooth with gradual transitions between maxima and minima. This suggests that the surface properties do not vary dramatically across the object. It is not covered in patchy ice or bright mineral exposures. Instead, it presents a relatively uniform exterior consistent with long-term space weathering. He notes that the phase of the light curve, how brightness changes with viewing angle and illumination, can further refine shape models. While data remain limited, the available observations do not demand complex geometries. Simple elongated shapes reproduce the measured patterns adequately. This simplicity is important. It means that interpretations do not rest on finely tuned assumptions. The object behaves as expected for a solid body shaped by gradual processes. The possibility of contact binary structure is also considered. Some small bodies consist of two lobes gently joined. Such forms can produce distinctive light curves. In this case, evidence for a pronounced neck or dual lobes is weak. If present, the lobes would need to be similar in size and smoothly connected. Again, nothing in the data requires invoking this structure, though it cannot be ruled out entirely. The guiding principle remains restraint. The simplest explanation that fits the observations is sufficient. He considers how rotation couples to thermal behavior. As the object turns different regions, heat and cool, if the shape were extreme or the surface highly variable, this could lead to uneven thermal emission and detectable forces. The lack of observed non-gravitational acceleration suggests that any such effects cancel out over a rotation cycle. This cancellation is more likely for symmetric or smoothly elongated shapes than for irregular ones. The long-term evolution of rotation also offers insight into age. Young fragments often retain high spin rates from their formation events. Over time, internal friction and external torques tend to moderate these rates. The object's rotation appears settled, not extreme. This points to a long period of evolution since its last major disturbance. Rotation becomes another clock ticking, slowly marking the passage of time through gradual change rather than sudden resets. He reflects on the connection between rotation and survival. Objects that spin too fast break apart. Objects that spin too slowly may be more susceptible to tidal deformation. Those that persist occupy a middle range. The object's rotation sits within this survivable band. It is neither stressed nor inert. It moves steadily, conserving angular momentum across encounters without accumulating dangerous extremes. The interplay between shape and trajectory also deserves attention. An elongated body experiences slightly different gravitational torques than a spherical one, especially during close encounters. These torques can alter spin states. The absence of chaotic rotation suggests that such encounters have been mild. The object's shape has not been leveraged into instability by strong gravitational gradients. This further constrains its past interactions. In the outward-to-inward narrative, rotation and shape occupy a central position. They translate invisible interior properties into observable signals. They also reflect the cumulative effect of environment and time. The object's shape is not a message or a mystery, it is a consequence. It emerges naturally from known processes acting over long durations. As the object continues its journey, rotation remains constant. There is no sign of rapid evolution. Each turn repeats the last with only minimal variation. Observers capture these repetitions and translate them into models, each one a step closer to understanding. The object itself remains indifferent. It spins because it must, carrying with it a shape that has proven adequate. He recognizes that this layer of understanding reinforces everything that came before. The object's calm behavior, stable motion, and material resilience all find expression in its rotation and form. Nothing here demands reclassification or special pleading. The object remains unusual only in how cleanly it fits within the expectations of physics applied patiently. The light curve fades as the object moves farther away. Measurements become harder. Rotation continues unseen. Shape remains fixed. The information gathered is finite but sufficient. It closes another circle in the analysis, linking outer motion to inner structure through the simple persistent act of turning in space. He's now farther from the Sun than the orbit of Jupiter, and the silence around him grows thicker rather than emptier. In this region, the solar wind thins, the pressure of light weakens, and the familiar architecture of the inner system loosens its grip. Dust grains drift with less urgency. Magnetic fields stretch and relax like long breaths. Here, trajectories that once seemed inevitable begin to reveal their subtleties. He does not hurry. He observes how order expresses itself not as rigidity but as persistence. The object known as 3I/Atlas moves through this space with a composure that draws attention, precisely because nothing dramatic is happening. There is no tail flaring into sudden brilliance, no chaotic shedding of ice, no frantic response to diminishing warmth. Its motion remains smooth, its path coherent, its rotation steady enough to be inferred across long intervals. In the quiet beyond Jupiter, most captured objects betray their histories through irregular spins or fractured surfaces. This one does not. Its light curve suggests symmetry. Its brightness variations repeat with a patience that feels almost deliberate. He considers the mathematics of torque, the countless small nudges delivered by uneven outgassing or solar radiation. Over millions of years, these forces usually leave scars in motion. Yet here the scars are absent